Today we're going to review some of the concepts from grade 9 chemistry, just to make sure we're all on the same page before we go into what we're going to cover for grade 10. So we're going to start with how we classify matter. And remember from grade 9, we talked about matter and we said matter is anything that takes up space and has mass. So of course matter is all around us. And in science, you may have noticed that we like to classify things. We like to identify, to organize. So we're going to classify matter a little further. And we've got kind of two branches that we can talk about. Matter that contains more than one kind of particle, or matter that contains only one kind of particle. And so if we're talking about matter containing more than one kind of particle, we call that a mixture. And there are many different kinds of mixtures, remember from grade 9. But if there's only one kind of visible particle, we call that a pure substance. So matter can be classified as mixtures or pure substances. And then, of course, within these two broad categories, mixture and pure substance, we can further divide down. So in a mixture, if we can see two or more distinct phases, if that matter's non-uniform, you can definitely pick out the parts. We say that that is a heterogeneous mixture. And if that mixture looks like one distinct phase, it's all uniform, it's all kind of one part, then we say it's a homogeneous mixture. And so those words are kind of important, and the prefixes kind of tell us everything we need to know. If the prefix is hetero, that means different. So there's two or more distinct phases, non-uniform, you can definitely see different parts. Homo, the prefix, means the same. So in a homogeneous mixture, everything looks the same. So what would be some examples of this? Heterogeneous might be something like sand and water. You can see the sand, you can see the water. They're distinct phases, they're not uniform. It might be something like salt and pepper. It might be a pizza where you can see the pepperoni and the cheese and the sauce and the onions and the peppers. You can see those distinct phases. You can see all the different parts. So remember, different, heterogeneous. Homogeneous all looks the same. So this might be something like sugar and water. You can't see the sugar particles once you mix them together. They dissolve, and so they form a solution. And it looks like one distinct phase. It's all uniform. It just looks like water, even though it is a mixture of sugar and water. Another example might be milk. I mean, milk has fats in it, has sugars in it, but to us it just looks like one uniform white liquid. And it all looks the same. That's the homogeneous part, the homogeneous mixture. Okay, and then if we look into pure substances, we can further classify those down. Which pure substances cannot be broken down to anything simpler? Well, that's anything on the periodic table. Those are your elements. So any element on the periodic table is a pure substance that cannot be broken down. It's already in its simplest form. And if we take those pure substances, those elements, and we combine them in fixed ratios, then we have a compound. So elements and compounds are pure substances. So an element might be gold, it might be silver, it might be sodium, it might be chlorine. And if we mix those together, we might get things like NaCl, salt. We might get H2O, water. Those are fixed proportion ratios of elements. And so water is always 2 hydrogens and 1 oxygen, H2O. Salt, sodium chloride, is always 1 sodium, 1 chlorine. So those are compounds. And then anything on the periodic table are your elements, and those are your pure substances. Mixtures, we can see definite differences in heterogeneous mixtures, different phases, they're not uniform, or the mixture all looks the same in the homogeneous side. Okay, so that's how we classify matter. And in grade 9, we kind of looked at these different parts of matter. In grade 10, we're going to focus on these elements and compounds and how they react. So speaking of the periodic table of elements, we need to review a little bit. Remember that the periodic table was organized originally, the original periodic table was described by Dmitry Mendeleev, a Russian chemist, and he took a look at the known elements at the time. There's only about 60 or 63 of them. And he said there's got to be some sort of connection here. There's got to be some sort of pattern between these elements. So he started placing them in different arrangements. And one arrangement that he looked at is what happens if I place these elements in order of atomic mass. So they knew the atomic mass at the time. And he could place them in order of increasing atomic mass. And when he did that, he kind of saw trends appear within these elements that were known at the time. And he saw that similar elements that shared similar properties started to group together in this kind of arrangement. And he actually was so sure about his table that he left blanks. He left spots open in the table. And he said, there haven't been elements invented yet that are going to fit in this spot, but I'm going to leave this gap. And I guarantee that someday elements will be discovered that fit the properties of this particular spot. And he was right. And so as we found new elements, they did fill in the gaps that he left. And so he had great insight into how these substances were behaving and how they should be arranged. And for that, we recognize him by naming element 101 after him. It's mendelevium. So today we don't use atomic mass to arrange our periodic tables, but we use atomic number, and that reflects the number of protons in the element. So when we look at our modern periodic table, we see these rows and columns. And so the horizontal rows that go left to right on the periodic table are called periods. And if you take a count on your periodic table, you'll see that there are 7 periods in the periodic table. There are 7 horizontal rows. And we also take a look at the vertical columns. They mean something as well. So the vertical columns have 2 names. They're called groups, or they're called families. And just like in any family, elements that are within those vertical columns share similar properties. In your family, you share traits with your siblings. Elements in the vertical columns share chemical and physical properties with each other. And if we take a look at the vertical columns, you can see that there are what we call 8 main groups, 8 main vertical columns. And we're kind of taking out those transition metals in the middle, and we're just kind of looking at the 8 main columns. But in total, there's actually 18. And as you go on in chemistry, you're going to take a look a little more closely at those transition metals. We will a little bit this year, and you'll do so more in grade 11 and 12. If we take a look at those 8 main columns, 8 main groups or families, some of them have names. Remember that first column are known as the alkali metals. They're very reactive. We watched that video in grade 9 of the reactivity with those metals in water. And so this will be something like lithium and sodium. And so we mix those with water. Remember, the video showed us increasing reactivity. So lithium was just maybe a little bit. If we put that metal in water, it kind of will move quickly along the top, maybe a little bit of smoke. And as we go down that column with sodium, and as we get even to cesium and rubidium, you see a much more violent reaction. So group 1 alkali metals are really reactive. They're one of the most reactive groups on the periodic table. And there's a reason for that when we look back at what their Bohr-Rutherford diagrams look like. All of these alkali metals have only 1 valence electron, 1 electron in their outer energy level. So remember that all elements want to be stable. So to be stable, you have to have that full outer energy level. And normally that's either 2 or 8. So if you're an element with only 1 energy level, you're full at 2. If you have more than 1 energy level, then you need 8 in that outer one. And so the alkali metals, they all have 1 valence electron. And so they're so close to being stable. They just need to lose 1 electron to be stable. And that's why these are so reactive. The second group we call the alkaline earth metals. They're also metals, they're also reactive, but they're not as reactive as group 1. So this would be your magnesium and calcium. We use those in reactions in grade 9. We mix them with acids usually. You saw some smoke and some heat come off of those, some bubbles. So they are reactive, but they're not as reactive as group 1. As we go across the periodic table all the way over to group 7, we have the halogens. So these would be things like fluorine and chlorine. They're also really, really reactive, because if you take a look at the Bohr-Rutherford diagrams of the halogen group, they've got 7 valence electrons. All they need is 1 more and they'd be stable. So halogens are really reactive. Group 1 alkali metals are really reactive. Halogens are really reactive because they're just that 1 electron away from being stable. So again, these are the 2 most reactive groups in the periodic table, group 1 and group 7. The last group is already stable. Their valence shell, their outer electrons are full. So they already have either 2 if they're neon, or 8 if they're 2 if they're helium, or 8 if they're neon and argon. So they already have that full valence shell. They don't need to react to become stable, and so they tend to be what we call inert, unreactive elements. So when we look at the periodic table again, we kind of separate it into three general categories. Most of the periodic table, those elements conduct electricity well, they conduct heat well, those are metals. So most of the periodic table is comprised of metals, and mostly on the center to the left side of the table. The right side of the table are the nonmetals. They don't conduct electricity and heat well. So metals would be things like your magnesium and your calcium and your copper and your gold. The nonmetals would be things like your oxygen and your nitrogen and your chlorine and your neon. Those are all nonmetals. They're not conductors. And then in the kind of separating the two is this group that kind of forms like a staircase in the periodic table. It's that group that kind of can have properties of either metals or nonmetals. So we call them the metalloids, and that kind of depends on what kind of environment they're in and what kind of application they're being used in. So I want you to pause your video right now and take your textbook, and I want you to take a look at your periodic table in the textbook, and I want you to do the coloring. So your textbook shows the different colors, and I want you to use a legend and kind of show me what color you're using for the metals, and color all the metals that color. And then take a look at the nonmetals and color all the nonmetals a different color. And then carefully trace out the metalloids, that kind of step in the middle. And just be careful when you're doing that. Remember, hydrogen is a special group. It's what we call the group of one. It isn't a metal. Hydrogen's a nonmetal, but it's over here with the metals just because of its electron arrangement and its atomic configuration. It kind of matches these group 1 elements in terms of having one valence electron. So it's put over here, but in terms of chemical properties, physical properties, it doesn't belong here. So when you're doing your coloring, you remember to color metals, except hydrogen isn't a metal. So keep that as your nonmetal. Okay, so pause the video and just finish your coloring there. And so again, when we look at our periodic table, we have these main groups. So remember that first column, those are your alkali metals. Second column, alkaline earth metals. Seventh are your halogens, and eighth are your noble gases. So remember, in terms of reactivity, these alkali metals are highly reactive, but remember they do not include hydrogen. Hydrogen is that group of one. So when you look at alkali metals, when you think of alkali metals, it's group 1, but not hydrogen. And the alkaline earth metals, again, still metals. These are calcium, your magnesium, your beryllium. They're not nearly as reactive. They have 2 valence electrons, so they need to lose 2 to be stable. These ones only have to lose 1, so they're much more reactive. Same with halogens. They only have to gain 1 to be stable, so they're really reactive. The noble gases already have that full valence shell. They have all the valence electrons they need to be stable, so they're not reactive, they're inert. Okay, so then we started talking in grade 9 about atomic theory, and we figured out several scientists who contributed to our current atomic model. So the first guy was actually Democritus back in ancient Greece. And remember, Democritus talked about these tiny indivisible particles that he called atomos, and that's where we get the word atom, which means indivisible. Then John Dalton, a teacher, came along, and he started describing matter as small particles called atoms. So we got that. And then he started saying, here's what's true about atoms. Atoms cannot be created or destroyed. And this is going to be important when we talk about reactions this year. So we're going to talk about something called the law of conservation of mass, and that means we can't just create atoms or destroy atoms in chemical reactions. We can rearrange atoms, but we can't create them or destroy them. So that's going to be a kind of an important point that we look at this year. All atoms, John Dalton said, all atoms of the same element are identical. So if I have gold, pure gold, all the atoms in there are going to be identical in mass and size to all other gold atoms. But here's the thing, they're going to be different in mass and size from the atoms of other elements. So he's saying that it's the atoms that make these things unique, that give them their properties. So if I have silver, the size and the mass and the properties of the atoms of silver are going to be different than the size and the mass and the properties of the atoms of gold. So those atoms are what give these elements their unique properties. He also said, Dalton said, when atoms of different elements link together in fixed proportions, they form compounds. So we're going to take a look at compounds today. We did this year. We did in grade 9 as well. We talked about ionic and we talked about molecular. We're going to continue that in grade 10. We're going to expand it a little bit. We're going to tell you about more compounds than we did in grade 9. Moving on from Dalton, we had Thomson. Remember, Thomson worked with cathode ray tubes and some gases. And doing his experiment, he found that there are these negative particles that we call now electrons that make up atoms. Then came Rutherford. Rutherford had a really famous gold foil experiment. You remember that famous one? He put the particles, the radioactive particles, in a lead box. He allowed a small opening, and he allowed those particles to fire at a very thin piece of gold foil. And we would expect, and they expected at the time, that all the particles would just fly through it because atoms are mostly empty space. And it's true that many of them did. But what was shocking is that some of them bounced back. And they kind of compared that to what would happen if you shot a bullet at a piece of tissue. You would not expect the bullet to bounce back. And they did not expect these particles to bounce back off the gold foil, but they did. They bounced back and they also deflected. And so this told Rutherford that atoms must have this dense positive nucleus that's interacting with these particles and allowing them to be deflected or repelled. So he gave us the idea that atoms have a nucleus. Thomson gave us the idea that atoms have negative charges. And now Bohr came along and he looked at those negative charges that Thomson was talking about. And he said these electrons occupy energy levels. Sometimes they're called orbitals. So they occupy these things around the nucleus. And so these scientists contributed to our current model of what we have of the atom. And we have this idea that you have this central nucleus, and it's a positively charged center. And then around the nucleus, you have these energy levels that contain these negative electrons. And those negative electrons are kind of orbiting around the nucleus, like planets would orbit the sun. So this is our current model, and this is the scientists that led us to that. And now understand in science, like in any other theory, the atomic theory can change as technology advances and we have more information. We might tweak this model a little bit. I think the basics of the model will stay the same, but we might find out more about, what are protons and what makes these up, and how are these moving. So we might find more information about this model, but I think that basic structure is going to stay the same. So if we look at the atom, we can kind of break down these particles. So we call the proton, the electron, and the neutron subatomic particles. They're the particles that make up the atom. And so we know a few things about them thanks to these experiments. So we know that the proton, think P for proton, P for positive. So the proton's positive. We know that from Rutherford's gold foil experiment. We know the protons are in the nucleus. We had that dense positive nucleus. And we assign it a relative mass of 1 atomic mass unit. And so if we want to compare that to the electron is found in those energy levels around the nucleus, like Bohr was talking about. They're the negative charges. We know that from Thomson's experiments. And we know that the electron has very little mass. It doesn't contribute much to the mass of the atom. We say the mass is negligible. Later on, they found that the nucleus has to contain more than the proton. The mass suggests that there's something else there. So later on, Chadwick found what we now call the neutron. It's located in the nucleus, along with the proton. It has no charge, so we say it's neutral. So neutron, neutral. Proton, positive. That leaves the electron to be negative. And we also give it a relative mass of 1. So you can see that the mass of the atom is taken up. When we talk about elements, we look at atoms and we want to draw Bohr-Rutherford diagrams, we have this way of writing, and it's called the standard atomic notation. Okay, so standard atomic notation, you want to remember that term. And that's really just this way of writing. Short form, it's kind of a short form way of writing about the atom. So what does this mean? Well, C is the chemical symbol for carbon. So we have a chemical symbol as part of the standard atomic notation. The 12 we call the atomic mass. Okay, so that's the protons and the neutrons. The 6 is the atomic number, and that's just the number of protons. So the mass number is the number of protons plus neutrons. The atomic number is the number of protons, and that's important to remember. Okay, so the mass number, the number of protons plus neutrons. So for carbon, that's 12. The atomic number, which is just the number of protons, for carbon, that's 6. And if you take a look, on your periodic tables, then you will see that the atomic number is written in the top left, and usually the mass number is written underneath the chemical symbol. And so again, if you're given the standard atomic notation, you can figure out information that'll help you draw your Bohr-Rutherford diagram. So if I look at this, I know that the number of protons is reflected in my atomic number. So I know the number of protons for carbon is 6. I know in a neutral atom that the number of protons is equal to the number of electrons. So also I can figure that the number of electrons is 6. And I can also figure out the number of neutrons. So remember we said 12 was the mass number. So remember the mass number is always protons plus neutrons. So if I know the protons plus the neutrons is 12, and I know that the protons are 6, then what I need to do is take the mass number minus the number of protons, and that gives me the number of neutrons. So now I have all the information I need to draw my Bohr-Rutherford diagram. So how do I go about drawing the Bohr-Rutherford diagram for carbon? Well, remember a few rules. The first energy level, the first orbital, can hold 2 electrons. The second can hold a maximum of 8. The third can also hold 8 for our purposes, although when you get to grade 11, you'll learn that it also actually can hold a maximum of 18. So I know what I can fit in each energy level. What I need to do for drawing my Bohr-Rutherford diagram is kind of remember, okay, I know in carbon, my protons were 6. My electrons, because in any neutral atom, protons equal electrons, positive charge equals negative charge to give you a neutral. And my neutrons in this case was 12 minus 6, my atomic mass minus my atomic number, so it also turned out to be 6, but remember that doesn't happen in all elements. It doesn't always work out to the same number. So when I'm doing my Bohr-Rutherford diagram, maybe I'll change color here. I'll draw the nucleus first. So draw your nucleus. And inside the nucleus are your protons. So we write 6p for protons and your neutrons. So the nucleus holds your protons and your neutrons. So kind of write that down so I know that you know it's in there. And then we got to show the electrons. And like Bohr said, the electrons are in these energy levels around the nucleus. So there's your first energy level. And we know that it can only hold 2 electrons. So you have kind of 2 choices here. I want to see your electrons as circles on the line. So you draw them on the line and then you color them in. So you can either show 2 electrons at 12 o'clock, or you can show 1 at 12 and 1 at 6. I will take either one, but no other position than that. So both at the 12, or 1 at 12 and 1 at 6. But now my first energy level is full. Remember, it can only hold 2. So now I have to draw, ooh, that's not very neat. Now I have to draw my second energy level. Turns out I'm equally artistic on video as I am in real life. So there's my first one. Okay, you've got your 2 electrons. I show them at 12 o'clock. Now you want to make your second energy level. Okay, so you make it nice and kind of circular around the nucleus. And this time I've got 2 electrons taken care of in that first, but I have 6 in total, so I have to fit 4 more electrons. I always start anything in the second, third energy level. You start at 12 o'clock, then you go to 3 o'clock, then you go to 6 o'clock, and then you go to 9 o'clock. You'll get a C/ if you don't do that. Okay, so that's kind of good form. So now I've got 1, 2, 3, 4, 5, 6 electrons. So I've satisfied my number of electrons for carbon. I've got 6 protons in the nucleus. I've got 6 neutrons in the nucleus. Okay, so all of that is now balanced with what I know to be the subatomic particles. And that is your Bohr-Rutherford diagram for carbon. And why do we draw that? We draw that so we can take a look at this valence shell of electrons. So I can see carbon has 4 valence electrons, 4 electrons in that outer shell, and that's going to tell me something about how carbon can behave and how it can form bonds with other elements. So this is important to be able to visualize, and that's why we like having this atomic model. Okay, so that's carbon. Now I want you to pause the video and I want you to draw the Bohr-Rutherford diagram for aluminum. So what I would start with is your standard atomic notation. So here's aluminum. And so if you look on your periodic table, I think it has an atomic mass of 27 and it has atomic number of 13. And the atomic mass is always the bigger number. Okay, so whatever the bigger number is, that's the atomic mass. The smaller number is the atomic number. So when I'm looking at this, I want to know how many protons does it have? That's the same as the atomic number. So it has 13. How many electrons does it have? Well, it's the same as the protons in a neutral atom. That'll change when we talk about ions, but for now we're talking about atoms. And how many neutrons does it have? Well, that's your atomic mass minus your atomic number. So we'll have the 27 minus the 13. And that's going to give you 14 neutrons. Okay, so then when you go and you draw your Bohr-Rutherford diagram, you're going to draw your nucleus, and you're going to say, well, there's 13 protons, because I know those are in the nucleus, and there's 14 neutrons. Right, that's my nucleus. That's my atomic number, my number of protons. There's my number of neutrons, and that gives me my atomic mass of 27 in total, concentrated in the nucleus. Then I'm going to draw my first energy level. I can fit 2 electrons there. Remember, I have to do 13 in total. I have to go to my second. Ooh, that's not very nice. Energy level. And again, I follow 12, 3, 6. Do make yours neater than this. You can do it better with your pencil on paper. Okay, so I do 12, 3, 6, and 9 o'clock. But remember, my second energy level can hold 8. So I'm going to start doubling up now. So there's a partner. There's a partner. There's a partner. And there's a partner. So how many do I have in total now? I have got 8 and 2 is 10, but I need to fit 13. So I've got to go into a third energy level. Oh, this is hard to do on a computer. Okay, so there's my third, and I have to fit 3. So I'm going to go at 12 o'clock, 3 o'clock, and 6 o'clock. Okay, so again, this tells me something, and that's not a pretty Bohr-Rutherford diagram. Do a nicer one than that. But this tells me something. First, it tells me that valence shell is not full. That outer shell only has 3. It would like 8. So aluminum is going to be reactive. It's a reactive metal. It's going to try to do what it can do to get that valence shell full. In this case, it's going to drop the 3 electrons. So it's unstable, right? And it's also showing me where it can make some bonding here, okay? where it can react with other elements. So that's why we draw these Bohr-Rutherford diagrams, to get a view of what's going on with this element. Is it stable? Is it not stable? Is it going to react? Is it not going to react? How is it going to react? And this can give us that information by looking at what our valence shell is looking at. That's the electrons involved in chemical reactions. Okay, so that's kind of a quick review of grade 9, and we're going to build on that and expand on that as we go through the curriculum in grade 10. And if there's any of this stuff that you feel you need to review, then go back and take a look again. And if you need to, you can ask questions. You can email me questions on it. We're going to continue from here. We're not going to spend a lot of time revisiting grade 9, but if there's any issues you want to go over, you just let me know.